So today we're going to be continuing with WebGPU. Yesterday we got a simple window working. Let's run the application. Yep, here you go, a simple window with a clear function right here. Okay. Let me also, maybe the music is too loud. I'm gonna make it, yeah, this is better, I think. I don't like it when it's loud, so. So yesterday we did the surface, today it's gonna be the pipeline. So if you're familiar with OpenGL, you may remember using shader programs. You can think of pipeline as a more robust version of that. A pipeline describes all the actions the GPU will perform when acting on a set of data. In this section, we'll be creating a render pipeline specifically. What this means, basically, shader programs in OpenGL are sort of the same as pipelines. So for every new shader, the best idea is to put as much of the shader code as we can in one shader, and then create a pipeline from it. So yeah, basically a shader is sort of a pipeline. Shaders are mini programs that you send to the GPU to perform operations on your data. We do this to GPU because GPU has a lot of cores which can do simple processing stuff. Simple compared to the CPU, and they can do it really fast. There are many types of shaders: vertex, fragment, and compute. There are others, such as geometry shaders or tessellation shaders. So these ones, I've actually never heard of them, but they're not supported by WebGL. They should be avoided in general. For now, we're just going to use vertex and fragment shaders. Vertex fragment shaders, what are those? A vertex is a point in 3D space, can also be 2D. These vertices are then bundled in groups of 2s to form lines, or 3s to form triangles. Most modern rendering uses triangles to make all shapes, from simple shapes such as cubes to complex ones such as people. Basically anything. These triangles are stored as vertices, which are the points that make up the corners of a triangle. Yeah, for example, these three. The vertices, we use a vertex shader to manipulate the vertices in order to transform the shape to look the way we want it. The vertices are then converted into fragments. Every pixel in the result image gets at least one fragment. Each fragment has a color that will be copied to its corresponding pixel. The fragment shader decides what color the fragment will be. WGSL is just the shading language that WebGPU uses. For example, OpenGL uses GLSL. Spear 5 is for Vulkan. Yeah, you can see them here. HLSL. I've before worked with GLSL and HLSL, never with these ones. I use GLSL, in OpenGL, and HLSL in FNA, which is a framework for C#. The conversion is done internally, and we usually don't care about the details. In the case of WebGPU, it's done by a library called Naga. Note that at the time of writing this, some WebGPU implementations also support Spear 5, but it's just a temporary measure during the transition period to WGSL, and will be removed. Okay, adding the shaders. So I am gonna create a new folder here, probably, call it shaders. In here, let's create a shader.wgsl, right? Oh, okay, I need to install something. WGSL. Wait, I do have it. WGSL analyzer. Let's try this. It's weird. clip position is vector 4. Oh, okay, so it shows if there are any errors. That's nice. That's nice. It maybe doesn't suggest anything, but just showing that there are errors is also pretty good. So we also create, so we specify a vertex and fragment shader. As you can see, the word vertex basically means that this function is gonna be called in the vertex shader, and later on, yeah, the fragment is gonna be for the fragment shader. It's kind of similar. Okay, no, I don't know. So vertex and function vs main. We're later gonna specify the name of the function. Built-in vertex index in vertex index. I think it's gonna explain pretty well what all of this does later on, so if it doesn't, I'm gonna try my best to explain myself. So variable out, vertex output, let x be equal. Okay, so it's doing it this way. Okay, from what I remember, the one time I used this, at first it's not gonna actually use any variables. It's gonna calculate everything itself, which is not a bad thing, I guess, for showing off how shaders work. And what does this do? Okay, so and our clip position is going to be equal to vector 4 f32 x y 0 and 1, and we return our out. What is going to happen with this return is it's basically going to pass it on into the fragment shader. First, we declare a struct to store the output of our vertex shader. This currently consists of only one field, which is our vertex clip position. The built-in position tells WebGPU that this is the value we want to use as the vertex clip coordinates. This is analogous, I think, to GLSL's GL position variable. So basically this is a built-in, yeah, it literally says here, so no need to explain. Vector types such as vec4 are generic. Currently, you must specify the type of value the vector will contain. Thus, a 3D vector using 30-bit floats would be vec3f32. Yeah, in our case, we're using a 4D vector, I guess. So, the next part of the shader code is the vsMain function. We're using vertex to mark this function as a valid entry point for a vertex shader. We expect a U32 called in vertex index, which gets its value from built-in vertex index. Yeah, I think it's going to be covered later on. What is vertex index, clip position, and clip position is just position of the vertex. We then declare a variable called out using our vertex output struct. We create two other variables for the x and y of a triangle. The F32 and I32 bits are example of casts. I mean, yeah, the same exact casts can be used in normal Rust. Because WebGPU was made for Rust, it's like the WGSL code, the shader code for WebGPU is very similar to Rust as well. As you can see, the FN word, like the return arrow, is the same. And yeah, the syntax is alike, let's say. Actually, the only thing that I'm not getting is, why is this var? Is there such a thing? Oh, variables defined with var can be modified but must specify their type. Variables created with let can have their types inferred, but their value cannot be changed during the shader. So these are basically constants, sorta. Now we can save our clip position to out. We just return out and we're done with the vertex shader. We technically didn't need a struct for this example and could have just done something like the following. So it just returns a position. Okay. We'll be adding more fields to vertex output later, so we might as well start using it now. The next part is the fragment shader. So we specify again that it's a fragment shader, call it fs main. It's gonna take what we actually return. So we return out, which is vertex output. So it's gonna be a type of vertex output. And this is gonna return a location 0 vec 4 f32. I think this is the color. So we do return vec 4 f32 0.3. Yeah, this is the color that we're going to be returning. It's, as you can see, RGB A. So this is the alpha value. It's transparency. This is hard take. This sets the color of current fragment to brown. Notice that the entry point for the, let's not do brown. I know this is not the main thing for this, but let's not make it brown. I don't like brown. Notice that the entry point for the vertex shader was named vs main, and that the entry point for the fragment shader is called fs main. In earlier versions of WebGPU, it was okay for both these functions to have the same name, but newer version of the WGSL spec require these names to be different. Therefore, the above mentioned naming scheme, which is adopted from the WebGPU examples, is used throughout the tutorial. This is a good practice overall, so it's easier to distinguish in the future. The location bit tells us WebGPU to store the vec4 value returned by this function in the first color target. We'll get into what this is later. Something to note about the built-in position. In the fragment shader, this value is frame buffer space. This means that if your window is 800 by 600, I think our window is... Oh yeah, we have default attributes. So like if we set the window attributes to... Is it here that it is created? Just a second. So, where are we setting this? It creates a window with window attributes. And window attributes has inner size. Oh yeah. So if we do window attributes.inner size, going to be equal to size new and let's say 400 by 300. Take that again. What? Why can't I just set the size normally? Inner size is an option of size. Maybe we need to do sum. Yeah. But still, it takes two. I mean, it takes one argument, but two are passed. Oh, this function takes one argument. Does it need a tuple? Trade. And just do physical size from. Wait. New. Width and height, yeah, 400 and 300. And this is supposed to be wrapped in sum, as it takes an option value. And it still doesn't work. size from, is this gonna work? If this is not gonna work, I'm just gonna okay, yeah, I'm just not gonna bother with it. Basically, it takes the status of our surface. This can be useful if you want to know the pixel coordinates at a given fragment, but if you want the position coordinates, you'll have to pass them in separately. Okay, I mean, we're not going to be doing this right now, so. Right, yeah, we're not going to be doing this right now. How do we use the shaders? This is the part where we finally make the thing, the title, the pipeline. First, let's modify state to include the following. Let's go to our state. Also, I wanted really quickly to clear everything that we're not using. Like this, what else? This shader module. I don't know how these even appeared here. That's fine. Okay, I don't need these guys here. Okay, here it's just delete these guys and this. Oh, yeah, you don't need these. I'm just doing some code cleanup with, oh, and a window as well. Okay. And here we don't need any of this. Okay. So now let's start with creating the render pipeline. It's gonna be a WebGPU render pipeline. I think we already specified. No, I think I'm gonna keep it like this. Okay, so here we also have to create. So let shader equal device dot create shader module. WebGPU shader module descriptor. Label is gonna be our share source WebGPU shader source WGS. Wait, does it have anything else? It has dummy, whatever that might mean. Okay, but we're using WGSL, so we specify that. And we do a macro include string. Of the file path is going to be shaders, because I think include string is a relative path. So include string and dot enter here. Okay. So let's see, include string. The file is located to the current file, similar to how modules are found. Yeah, okay. And don't forget this here, of course. And we pass in. Actually, no, we cannot pass it yet, because we have to create the pipeline. I think it's gonna be better. You can also use include WGSL macro, the shortcut to create the shader. Yeah, sure, why not? I think I'm gonna do that. So we call device create shader, device create shader module, and it's include WGSL and shaders shader WGSL. Also, because in the end we're gonna have to get a render pipeline, so I'm gonna make a let render pipeline be equal to create state render pipeline. so we can keep the same style going as we did yesterday. Let's close all these. Function create state render pipeline. So any arguments that I would need to pass in specifically? I don't think so. It returns a WebGPU render pipeline. So let me just cut this line here. Okay, so create a shader. I mean, we can specify the path, I guess. Yeah, sure. This takes in I think I can pass in the path like a string, and then shaders shader dot WGSL. Right, and then put in the path here. Or does it need to be a constant or something? String literal. Okay, so I think this is what it means by string literal. To string. Oh, I need to do so. Okay. Device. Oh yeah, we need to pass in device. So device is gonna be a borrowed device. Let's see. After the path, we also pass in the reference to our device. Okay. Path. Consider borrowing here. Expect a string literal. Okay, fine. Maybe in one of my older projects? Should I waste time on that right now? I think I should. Let's see. Open folder. If we go to Rust, I think it was SNA, this thing. Here we go to pipeline. Shader file name is type string. So let's see. Source code is fs read to string of the file path. Okay, let's try this. So this was a while ago, so it might not work anymore. So we create, we pass in, what do we pass in? We pass in a file path, which is a string. Then we use that file path to create shader src. It's going to be equal to fs read to a string our file path, and would accept failed to read. I think I'm gonna use format here, actually, now that I remembered about this, so I can use variables file path. Right, can I use that? Expected borrowed string found string. Oh, it meant like, or did this have an error? Wait, if I do this as string. Yep, no, it's still. Okay, I guess for now I'm just gonna print out the message. Failed to load shader. Exclamation point. Right, I cannot use. Yep, a message just a borrowed string. Our shader. And the source is going to be WebGPU shader source WGSL And we do shader src and int. Okay, this seems to work. Let me know path. Does it not like? Quick fix to owned. Oh, and also, yeah, don't forget the device. Okay. I can now close this and continue. So then we create a layout for the render pipeline. Oh, one more thing, we need to create a pipeline layout. We'll get more into this after we cover buffers. Finally, we have, okay, we still don't have this, we need to create render pipeline layout. It's going to be device, not create pipeline layout. Description is going to be WGPU pipeline layout descriptor. Label, some name, render pipeline layout. Okay, these are going to be set later, from what I remember at least. So for now, let's just some maybe other variable which is not here. Expected, oh, forgot to do a borrow. Let render pipeline equal device dot create render pipeline with borrowed WebGPU render pipeline descriptor. So label, label is going to be some render pipeline, of course, just a normal name. We don't have multiple of them right now, so there is no reason to give them to give it a specific name like render pipeline triangle or something. Okay, so we pass in the vertex. This is the vertex shader. So vertex state, the module, that is our shader, because this is called a shader module. Yeah, as you can see, we create a shader module here. So we pass in the shader. We then specify the entry point. VS main, this is, if you go to our shader, it's this. So it's the name of the main function in the vertex shader. Pass that in. Targets is a list of, oh, I'm looking in the wrong place. So then buffers, that's an empty list for now. Compilation options, WGPU pipeline, compilation options, default. Okay, that's it for the vertex shader fragment. Oh yeah, this has actually been updated, because the last time I tried to go off this was not here. Yeah, that's cool. I actually had a problem with that, because I was trying to figure out for like the longest time why it wasn't working. And yeah, turns out the solution was pretty simple. Okay, so it's targets, some WGPU color target state. The format is config.format, and blend is some WGPU blend state replace. I think there's like add, multiply, Or it's just alpha, okay. Replace. I wonder if you're doing replace here, does that mean that we cannot have transparency? I'm gonna have to test that out real quick after we get our triangle drawing. Color writes all. Describes the color state of render pipeline. Okay. So after this we put a comma and compilation options again default. Because like this is very specific. I think this is as specific as I had a thing somewhere here before. Let me just search for it. Yeah, memory hints. I think this is just something very specific that we're probably, oops, I closed it by example, that we're probably not gonna use, but I might as well be incredibly wrong. So config. There's not no config in here, so we also could pass in the config, really? Okay. Config is the config. Surface configuration, yep. Let's see. I think we can remove WGPU surface configuration here, but I don't really know. Let's see. So in here, when we call this, we also pass in a reference to our config. Oops, I forgot to add reference here. Where's this? Yep. This. I think I can make this a little bigger. Okay. What's wrong with this? Oh yeah, we're still not returning anything. I think... Oh my god, I'm lost. Okay, yeah. This is everything. So we created several things to note here. Here you can specify which function inside the shader should be the entry point. These are functions we marked with vertex and fragment. Yep, let me open and show this. Yeah, for example, we marked VS main with vertex and FS main with fragment. The buffers field tells WebGPU what type of vertices we want to pass to the vertex shader. We're specifying the vertices and the vertex shader itself, so we'll leave this empty. We specify, yeah, as we did here basically. I think I said something about it earlier, but I'm not 100% sure. And there's some stuff that we're gonna add here later. Can you use the to-do macro in this scenario? And nope, doesn't seem like you can. Let me just fill out these fields. Quick fix, fill structs. Oh, there are a lot of them. Okay. The fragment is technically optional, so you have to wrap it in some. We need it if we want to store color data to the surface. The targets field tells WebGPU what color outputs it should set up. Currently you only need one for the surface. Targets is, yeah, some color targets, format, the format we use for the creation of the surface. And blend state, replacing, which I think means no alpha stuff, which I'm gonna check on later. Write mask, and it writes to all. Okay, right? Mask, which enables disables writes to different color alpha channels. Okay, so it writes the color to all channels. Let's see. The targets field tells WebGPU what color output should have. Currently only has source. Okay. We'll talk more about color state when we talk about textures. Oh, textures is not so. But okay. The primitive field describes how to. Oh yeah. Let me just read this. The primitive field describes how to interpret our vertices when converting them into triangles. Using primitive topology triangle list means that every 3 vertices will correspond to one triangle. Okay. I mean, this is usual. I think GL has something like, I don't know why I remember this, but GL draw triangle. I think there was a function here which also did the same thing, that it specified somewhere here. I don't know exactly where. Yeah, I cannot find it. That's fine. It's not the point right now. So the front face and cool mode field tells you how to determine whether a given triangle is facing forward or not. Front face counterclockwise means that a triangle is facing forward if the vertices are arranged in a counterclockwise direction. The triangles that are not considered facing forward are cooled, not included in the render, as specified by cool mode back. We'll cover cooling a bit more when we cover buffers. Does this mean that it's a collision cooling by default? Or what does this mean? Maybe it does. Okay. So primitive. It's a WebGPU, primitive state. Our topology, we're going to be specifying triangle vertices. Vertices. Indices. Okay, strip index format, none. Front face. So this is how we're gonna write our vertices. Like they're gonna be counterclockwise. So it's like, if we let me open Paint. So for example, if you have a triangle, counterclockwise there is that we're first gonna write this vertex, then this one, or maybe this one first, then this one, then this one. You get the point. If we said clockwise, then it would have to go the other direction. I think at least that's what it means. Okay, so cool mode is WebGPU cool mode. Oh, just front face, okay. Front face back. Polygon mode, WebGPU, polygon mode fill. Okay, this is okay. I'm gonna show this later. Some really cool stuff you can do with this. Unclipped depth false. And conservative false. Oops, none like this. Oh, front face. It's front face. Oh yeah, it's just face. Okay. Then we create the depth stencil. Oh, we create everything else. We're not using a depth stencil buffer currently, so we leave depth stencil as none. This will change later. Yep, this will change later. So we can do layers and stuff. Because depth stencil issues. If we Google something like this, if we're not using our depth stencil, our program will not know what is in front and what is in back, so it's gonna look weird, because technically that cube is in the back, but it still sort of draws it like in the front. Yeah, it's a cool thing. But because we're doing 2D right now, just a simple triangle, we don't need it. Okay, multi-sample state. Count 1, mask. This is actually very specific. I heard you have to do something like this because of macOS or something. But I might be thinking of something else. They might say something about it later. So this is also to none. Let's see, errors. Okay, the errors are still the same. That's a good thing. Let me move this back like this a bit. count determines how many samples the pipeline will use. Multi-sampling is a complex topic, so we won't get into it here. Will it get into it in general? Probably. Okay, let's see. Alpha to coverage, mask specifies which samples should be active. In this case, we're using all of them. Alpha to coverage enabled has to do with anti-aliasing. We're not covering anti-aliasing here, so we'll leave this alone. Anti-aliasing, that sounds familiar. Oh, what is it? Anti-aliasing is a computer graphics technique that smooths jagged edges on curves and diagonal lines. Oh yeah, I think we looked at this yesterday. Or was it multi-sampling? Probably. Okay. I just got. Okay, so we return, we're gonna remove this and replace this with return. So now it should remove this error, right? No, okay, what is this again with the stupid file paths thing? Borrow of moved value, oh, I need to do it. Borrow here, and this is like this. Should I just use a... I think I'm just gonna use a normal string. I mean, by normal string, I mean that. And pass in here just this. Yeah, it seems to not scream at me, which is a good thing. So yeah, and then we just do render pipeline here. Okay. So this should be the render pipeline done, which means that shader loading is done. Yep. Doesn't seem like we have any errors. That's a good thing. That's always a good thing. Let's see what's next. So then we have to use the pipeline. We do rendering again here. Where is it? Yeah, render. Where we're creating the render pass. Now we're actually going to be using it, so yeah. I don't think we need to specify anything here. Yep. Oh, here. So before we submit the pass, we have to set our pipeline or set shader for OpenGL people. Self.render pipeline. And we also have to draw it. The amount of vertices is 3. And this is amount of instances. I think it's going to go into instancing later. Yeah, instancing. It's a very big part of graphics programming. It's an optimization thing, if you can say so. To draw something. Yeah. So this means is it creates a range between 0 and 3, so it's 0, 1, 2. And then it's going to use these values here, where we do built-in vertex index. So first it's going to get 0, do everything with that, then it's going to get 1, calculate it again, and that's going to give us points, which in return should draw a triangle, right? Nope. Some errors. Let's see. Maybe I forgot something. State. Since we cannot find the path specified. Let's see, what if I move it out? Will it treat it then? Okay. So this lies? Is this not correct then? Because it says here that it... Okay, it doesn't say it here. Oh yeah, maybe that's a thing. It doesn't say it there. Well, it's still better if I do it this way. To separate shaders from source code. So yeah, now we have a nice triangle. Oh, this is really good looking. I don't know why they chose this awful color. But before I continue, I wanted to show one really cool thing that I talked about yesterday, because I don't want to forget it. So, when we're creating our state, I think it's in creating the surface, or maybe the instance. No, these are the default backends. Oh yeah, where we have different features. So for example, let's say, because right now what we're doing is we're drawing, yeah, polygon mode fill, which means that we're filling in those points. I mean, we have 3 points basically, those 3 vertices which we generate in the shader, and then we're just filling space between them. We can do line. What this is gonna do is it's gonna return us an error, because, yeah, it's gonna say here probably, yeah, features polygon mode line are required, but not enabled in this device. So if we do features default, I think you can do and WGPU features line polygon line mode. Can you do this? Yeah, we can. I think this doesn't show an error there. Okay. Maybe it's this simple? Yeah. It's probably difficult to see, but instead of filling the shape, it only draws the lines. Another thing that we can also do. Oh yeah, by the way, to stack features you do this symbol. I forgot what it's called, but yeah. I think if we can also do features polygon mode point. Oh, I need to do this. If we do point, I mean it's probably pretty self-explanatory what is gonna happen. But it draws the points, which are incredibly difficult to see on stream. But there's one point here that I can see, and other points somewhere that even I can't see them. So yeah, they are there, believe me. So let's return this back to normal fill mode. And we're gonna go to buffers and indices, because in my opinion both of these should be one chapter, but they decided not to do it in one chapter. Don't forget to drink your water, by the way. So, let's see. This is way too big. Let me close this. Close all of this stuff. We're not going to be using it. Actually, no, we are going to be using this, but not right now. A buffer is a blob of data on the GPU. A buffer is guaranteed to be contiguous, meaning that all the data is stored sequentially in memory. Buffers are generally used to store simple things like structs or arrays, but they can store more complex stuff such as graph structures, like trees, provided all the nodes are stored together and don't reference anything outside the buffer. We are going to use buffers a lot, so let's get started with 2 of the most important ones, the vertex buffer and the index buffer. The vertex buffer. Previously, we've stored vertex data directly in the vertex shader. While that worked fine to get our bootstraps on, I simply want do for the long term. Yeah, we stored it in the shader. Yeah, like we did here. And it's not really storing, it's just creating them depending on the vertex which is being drawn right now. The types of objects draw will vary in size, and recompiling the shader whenever we need to update the model would massively slow down our program. Instead, we're going to use buffers to store the vertex data. We want to draw. Before we do that, though, we need to describe what a vertex looks like. We'll do this by creating a new struct. I don't really know where to create this, as I'm probably gonna do it state, like in the end here. So we do replicate C, derive, it's gonna be copyable, clonable, and debuggable. Struct, I'm gonna make it a public struct. Vertex is gonna have a position, so 3 floats, and a color. Oh, yep, before we continue, I also wanted to check out another thing. So, because here, when creating the pipeline, we specified that it's gonna be replacing. So if we change this to be like 0.5, it's not gonna be transparent, right? Yep, doesn't seem to be. But if we do this, it's probably gonna have some problems. If it's gonna have many problems, I'm not gonna fix them and just continue on. I think it's less visible, but I might be going insane. Let me make it really small to the point that it should be technically invisible. Oh, it does work. So yeah, if we do blending states to replace, it basically removes the alpha channel from here. And it doesn't remove it, you still need to use it, but it doesn't change how the pixel is going to be visually. Let's see, so we go back to vertex. Our vertex will have a position and a color. The position represents the x, y, and z of the vertex in 3D space. The color is the red, green, and blue values for the vertex. We need the vertex to be copy, so we can create a buffer with it. Next, we need the actual data that will make up our triangle. Below vertex, add the following. So, I am not gonna write this. These are just triangle vertices. Yeah. I mean, I can kind of explain how they work, I guess. If we go to paint, let's see. Let's get our trusty line tool and do something like this. So for example, it's gonna have points. If we say that this is the center, let me make this a bit bigger. We say that this is the center, so that's 0, 0. And this point is gonna be 0, 5. Actually no, first x, yeah, sorry. 0, 0, so like we see here. Because we are drawing a 2D triangle, we're not going to be messing with the z-axis at all. Then this point, see, because we did counterclockwise here, where is it? Counterclockwise, yeah. Front face, counterclockwise. These vertices are going counterclockwise, so first it specifies this one. Then it goes to the bottom left one, which would be minus 0, 5, 0, 5, and minus 0, 5. This one is going to be positive on the x, but as well negative on the y. So yeah, and the color is just going to specify which color each vertex is. So yeah, that's pretty explanatory. Self-explanatory. Yep. We arrange the vertices in counterclockwise order: top, bottom, left, top, bottom, right. We do this way partially out of tradition, but mostly because we specified in the primitive of the render pipeline that we want the front face of our triangle to be the WGPU front face counterclockwise. So that we call the back face. This means that any triangle that should be facing us should have its vertices in counterclockwise order. Now that we have our vertex data, we need to store it in a buffer. Let's add a vertex buffer field to state. So the vertex buffer, let's go up here. I wouldn't really recommend it doing like this, but again, they're showing it for one-time use. Probably when I'm gonna finish this and continue doing my own stuff here. Okay, so let's see. I'm not gonna add a function for creating a vertex buffer. We need to make it before the render pipeline though. Device.create buffer. It's a reference to WGPU utilities buffer in a descriptor. Label is going to be sum with vertex buffer, and then contents byte monk. Oh yes, we're gonna have to include this library. Gas slice of vertices. Usage, WebGPU, buffer usages, vertex. So it's gonna be used as a vertex. So this is gonna return an error. All we have to do is include a new library called bytemonk, which should cast them as references to U8 to like a. Why is it not showing it? Okay. Okay, so this is fixed by this error is fixed. There should be some lines that I need to copy. Oh yeah, here. So let me quickly go to our vertex. This should also derive from bytemonk pod, and bytemonk is zeroable. Then after this we implement them. I really don't know what they are. Oh, do I need to do features? Yeah. Let me go to dependencies dot. I'm gonna do it here. So it's version, latest version, and features are gonna be derive. So this should fix this issue. Or maybe not. Let's see. First, let's also specify this. Oh, it's already did it by itself. Oh, did I? Yeah, cast slice. To cast slice vertices, yeah. As a reference, as I said, the create buffer init method expects this and does that for us, and applying to your cargo file. Maybe it's some new version. Let me just use the older version. There shouldn't be a big problem with that, right? Seems as there is a big problem with that. Quick fix? No. Let me copy this. Yep, I don't know why that would help. First, let me return back to the newer version. Ugh. I experienced the same issues with bytemonk before. It's not good. I don't like it. What if we remove these two? Where's the error? Oh, in returning. Okay, what if we return, what do we call it? Vertex buffer. Yeah. Oh, really? Because I remember before I had to do this. I guess it got updated or something since then multiple times, so now it recognizes them. That's good. Less code, less bloat. So what do I do with it? We need to tell the render pipeline to use this buffer when we are drawing, but first we need to tell the render pipeline how to read the buffer. We do this using vertex buffer layouts and the vertex buffers field that I promised we'd talk about when we created the render pipeline. Vertex buffer layout defines how a buffer is represented in memory. Without this, the render pipeline has no idea how to make how to map the buffer in the shader. Here's what the descriptor for a buffer full of vertex. A vertex defines how a buffer is represented in memory. Without this, render pipeline has no idea how to map. Okay, so array stride, size of the vertex. The amount of memory we're gonna step is vertex attributes. Offset 0, shader location 0. This is useful from what I remember. Format, all of this is useful. Float 32 3 times. Wouldn't be, yeah, it's 2 times. Okay, yeah. Offset, because like this is for the position. And because the position goes first, there is a 0 memory offset for it. So it's 0. But then when it gets to color, we have to offset it by this amount, which is SCD memory size of S, yeah. Then shader location 1. This is also where we're going to be passing it to. Like the first location, this is to the, I mean, I guess this is the second location, this is the first location. Format, and yeah, also F32 times 3. Let's see, I think everything here is pretty explanatory, so I'm not gonna really read through this. Okay, yeah, except for number 5, the shader location. This tells the shader what location to store this attribute at. For example, location X, vec3 F32, in the vertex shader would correspond to the position field of the vertex struct, while location 1 would be the color field. Yeah. Well, let's create a static method on vertex that returns this descriptor. So let's go to our vertex and we're gonna implement here. Actually, no, let's do it here. Implement vertex function description. Vertex buffer layout is gonna have a static lifetime. So that means it's gonna exist the entire program. Static lifetime, WGPU, vertex buffer layout. Oh, okay, yeah, fine. Okay, array stride. So it's gonna be the memory size of our. This is actually a really cool thing I learned. This is called the fish syntax. I remember hearing about this in some random video about Bevy, the game engine, and I just remember that for some reason. Let me even Google this. Rust fish syntax. Oh, turbofish. Oops. Let's see. This is. We need more stuff here. So this is as WGPU buffer address. our step mode is going to be vertex attributes. Offset is 0. Shader location also 0. Format, WGPU, vertex, format, float, 32 times 3. Also offset is going to be SD memory size of WGPU for address. Shader location 1. Format is going to be the same format, so WGPU vertex format, float 32 times 3. Okay. Let's make this a public function though. Specifying the attributes as we did now is quite verbose. We could use the vertex array attribute array macro provided by WebGPU to clean things up a bit. With it, our vertex buffer layout becomes. Oh, this is nice. Let's see. Let's comment this out for now. And set our attributes to WebGPU. Reference WebGPU. Vertex attribute array. 0 float 32 times 3, and the second one is gonna be float 32. Yeah, same. And now this returns an error. Well, this definitely sees the result of vertex attribute array as a temporary value, so a tweak is required to return it from a function. We could make it const. Wouldn't this just be using more lines at this point? Okay, fine. Public const attributes type WebGPU vertex attribute 2, which is going to be equal to WebGPU vertex attribute array. Same thing. Let me copy this. And then we just use this here. Seems to be working. Okay, it is less verbose. Now we can use it when we create the render pipeline. So, in creating the render pipeline, let's close this up. We're doing this here. So, in vertex and buffers, we're gonna specify our vertex description. Okay, seems to work. Thing is that we're not using the vertex buffer yet anywhere. One other thing, actually, oh yeah, otherwise our program will crash. Or will it? Okay, it's gonna crash. I'm not gonna test it, I just wanted to clear the terminal. So let's see. Oh, state. And we go to render. And before we do the render, draw, do render pass. We set the vertex buffer, 0, self, vertex buffer dot slice. Okay, I'm kind of curious what this is. I think double dot in this case means that it's gonna go through every element. Return a slice of a buffer's bytes. Yeah. Okay. Okay, this is pretty... Oh, set vertex. I'm curious about what this 0 means, though. Maybe it says it's here. Slot. Takes two parameters. The first is what buffer slot to use for this vertex buffer. You can have multiple vertex buffers set at this time. Second parameter is the slice multiple. How would that work though? Like if you go to the we're gonna change the shader later. Multiple buffers, I guess from multiple objects. Because wait, let me go to where we create the vertex buffer. Some vertices. I guess if we create multiple vertex buffers, what does it mean by slot though? I would get it if we set vertex buffer then draw, then set another vertex buffer then draw. How would that even, would it like go through each one of them? Like if I had 2 vertex buffers? Like if I go to state here, like if I had another vertex buffer and I had it set to slot 1, for example, then it's gonna go on drawing, it's gonna go through this one, and then it's gonna go through this one. Maybe. So struct okay, now vertices. Okay, a little bit more up. Number of vertices, a year 32. So in here we do the number of vertices. I'm gonna put these two together. Yeah. And then we use those vertices, I think, from 0 to self dot number of vertices. Am I right? Yep. And still only one instance. Before our changes will have any effect, we need to update our vertex shader to get its data from the vertex buffer. We also have it include the vertex color as well. Okay. So the new shader, let's see what's changed. So first we have a new vertex input. Vertex input. Okay, location. That is actually the same thing as if you remember. If we go quickly to state, is when we are go down, yeah. Here, yeah, this is where we're setting, so the number 0, then 1, and yeah, it basically means this number in the location. So this is going to be 1, and this is going to be color of type, also vec32, like this. It's still clip position, I do not like that name, clip position. Okay, and it's gonna also return the color. Still a vec3 of type f32. Usually it's a vec4 here, and just returns it with an extra alpha thing added to it. But I guess it. Oh yeah, it does do it here. Yeah, it just does it in the fragment shader. I just see it be done in the vertex shader. So our model. Okay, let's delete this. We're not going to be needing this anymore. So vertex input, variable out. Out.color is going to be equal to model.color. Out.clip position is going to be equal to vector 4 f32 of model.position. I wonder why the clip position is in 4 dimensions. What is the fourth one for? Yeah, I really don't know. So it takes in the vertex output, returns. Yep, so it's gonna return vector 4 f32 of in and 1.0. So the triangle should be beautiful right now, unless I've done some mistake. Oh no, it is beautiful. Look at this. I wonder how it looks like in the line mode. Just like rainbow lines. I think that looks pretty cool. Yep, it sadly it's barely visible, but it still looks cool. So what I wanted to test out real fast. So vertices, and let's copy this and make vertices underscore 2. Here, let's just change the values a bit, like this is 7. Actually, let's... I don't just, yeah, random numbers. That's fine. I don't know, like, this is 0. But this is 1, this is 0, this is 1, and 1 here. Something like this. So then, we create a second vertex buffer, which is also a WGPU buffer. And in here, when we create the first one, we're also gonna set the second one. So it's gonna be vertices underscore 2, and this is gonna be underscore 2. And then here we pass in vertex buffer underscore 2. Okay, no errors yet. I think if you run this, nothing else should happen, right? Yep. But what we're gonna do now is instead in render, we're actually gonna see what this slot thing does, because I don't really know. So we copy this twice. And we do vertex buffer 2 dot slice. So this is going to be slot 1. And absolutely nothing draws. What if I set this to 1, but this to 0? Does it just draw the top? Oh yeah, it just draws the top slot. Okay, let me remove the second slot now. So remove this. Let's go up here, remove this, and remove this. Everything works. Let's see. If you run the project, Yep, everything still works. I'm gonna check something real quick. 1.5 hours already. Well, I'm almost done. Just some stuff left here. Okay, vertices. I am not copying these. I'm sorry. We definitely don't need an index buffer, but they still are plenty useful. An index buffer comes into play when we start using models with a lot of triangles. Consider this pentagon. It has a total of 5 vertices and 3 triangles. Now, if you want to display something like this using just vertices, we would need something like the following. Yeah, this is a lot of information. As we can see, ABE counterclockwise, BCE and CDE. Okay, like here. They're specified, that's where I'm reading them from. You'll note, though, that some of the vertices are used more than once. C and B are used twice, E is repeated 3 times, assuming that each float is 4 bytes, then that means of 216 bytes we use for vertices, 96 of them are duplicate data, and that is a lot of, just for a simple thing like this, that's a lot of data. So having this for like a model consisting of 1,000 different vertices is not a good idea. You'll note though, basically we store all the unique vertices in vertices, and we create another buffer that stores indices to elements in vertices to create the triangles. Here's an example of our pentagon. So now what's changed is we only have each point, A, B, C, D, E, yeah, counterclockwise, and indices. These indices, as you can see, they're separated into 3 rows. This is for readability reasons. So these basically indicate which index of this array, vertices array, is going to make the triangle. So it's going to separate, here it's separated into 3, just so it's going to be more readable. So in this case, just let's take a look at one triangle, A, B, E. This is first slot, second, index first, 0 index, index 1, and E is index 4. So here, this is the triangle, 0, 1, 4. Again, it goes counterclockwise. So yeah, this way we can specify in which order they're gonna go. So thanks to that, we saved 76 bytes. And this works exponentially. So the bigger your vertices is, the more you're gonna save data. So we also need to create an index buffer then. Yep. Let's go up here and then vertex buffer, create an index buffer. It's also going to be a WGPU buffer. If we go to, okay, let's move this down now. Let index buffer be equal to device, create buffer init. It's going to be a disk, so WGPU, U2, buffer, initialize descriptor, label, sum, index, buffer. The contents are gonna be mark cast slice of indices, and usage is gonna be for index. Okay, so we create the index buffer, and now we just need to also set it. Everything else seems to be the same. Okay, so now in the render pass, oh, it's still not here. Let's see, let me close this, we no longer need it. So after we set the vertex buffer, we also set the index buffer. So it's going to be self.indexBuffer.slice of all of them. WebGPU index format uint16. Yep. So this is also changed, because now that we're drawing with indexes, we have specified that it's a indexed draw, so this stays the same, so number of, oh my god, self, not number of vertices, base vertex, so it's the first one is 0, and amount of instances is still 1. Yeah, when using an index buffer, you need to use draw index. The draw method ignores the index buffer. Also make sure you use the number of indices, not vertices. Oh, I almost did that mistake. Oh, okay. That's on me. So I guess I'm gonna put this here and this here, even though this is sort of useless now, but just in case we're gonna keep it. So number of indices, let's put it here as a U32 and also return it. Okay, so now that this is done, specify this to number of indices. Okay. Yes, we did this. And we should draw it. The color red, green, yeah, it is pink. So all of this should be pink. Yay. Color correction. If you use a color picker on the magenta pentagon, you'll get a hex value of, okay, if you convert this to RGB values, you'll get 188.0188, dividing these values by 255 to get them into the 0 to 1 range, which is used here to setting colors. It's roughly 0.737, and as you can see, that's a big difference. That's like a whole 2/10. This is not the same as what we're using for vertex colors, which is 05005. The reason for this has to do with color spaces. Most monitors use a color space known as sRGB or standard RGB. Our surface is most likely depending on what is returned from surface.get preferred format. Using an sRGB texture format, the sRGB format stores colors according to... I think I'm not using surface.get preferred. Yeah, I'm not using this. I am using and creating a surface. Oops. So that, wait, where is it created? Nope. Wait. Formats, where am I getting formats? In the config. Here. So let's see. Yeah, I just get the first one. You get the correct color by using the following formula. Do this with an sRGB value will give us a little off from this value. Instead of doing a manual color conversion, you'll likely save a lot of time by using textures instead, as if they are stored in an sRGB texture, stored, I guess they wanted to say. The conversion to linear will happen automatically. We'll cover texture in the next lesson. I don't think I'm going to be doing color conversion right now. See what it's on about then. Well, okay, I guess tomorrow we're going to continue with making textures. A beautiful PNG, as you can see here. But for today, I think that's going to be it, as I'm already tired. So, yeah. Thanks everyone for coming. See you tomorrow. Probably. Hopefully. You never know what's gonna happen. Bye bye.